France, and he's an expert on conformal field theory and statistical mechanics, especially the connections between them, the algebraic connections. And he's going to talk about conformal field theory and associative algebras.
Thank you. Well, it's a pleasure to be here. I'd like to thank the organizers, as is customary. I'm a physicist, which means my talk will not have a single theorem, but I'm not really a physicist, so my talk won't have any experimental curve either. I'll be in no man's land, and I was looking for a nice citation from a Cambridge man, and of course Bertrand Russell has always a lot of citations you can use. So here's one I like. Physics is mathematical not because we know so much about the physical world, but because we know so little. It is only its mathematical properties that we can discover, and that's definitely a good summary of what this talk will be about. So the talk is really about CFTs and associative algebras, and there'll be two parts. One is kind of a summary of what the situation is, what the motivations are, and then there'll be a slightly more technical aspect which I want to discuss towards the end, mostly because we need help from mathematicians on various aspects which are too hard for us, I guess. All right, so I'll start with CFTs, and I will try to explain why physicists, in particular people doing CFT, are interested in associative algebras. So for us, conformal field theories are useful for various reasons, and one of them is that they allow us to tackle critical phenomena in statistical mechanics, and Vaughan Jones gave a nice introduction to what a critical point is in real experimental physics. Thanks for that. So I can move right away to models. And you all know about the Ising model, you all know about percolation. Let me remind you very briefly what these models are made of. They are made of degrees of freedom on a lattice, like spins, taking values plus or minus 1 in the case of the Ising model, or in the case of percolation, you're having edges of the lattice which are occupied or not with probability p. And then there is the concept of a Boltzmann weight of a configuration, which is typically an exponential of something we call the energy, and the energy is a function of the variables. So in a nutshell, we have a probabilistic problem where configurations of spins or configurations of bonds have a certain probability, and we are interested in calculating properties of some observables in this setup, which may depend on an external parameter like the temperature T or the probability P. Some quantities may be trivial, like for instance in percolation, it's well known that the partition function, which is the sum of the probabilities of all the events, is just equal to 1. So this is a two-dimensional point of view, by the way. Vaughan was mostly toying between going between 2 dimensions and 1 dimension, the quantum and the classical. I will refrain from doing this. I will essentially only discuss 2 dimensions. Now, these statistical mechanics models usually are not very interesting, but it happens that they have critical points where the physics becomes non-trivial. In particular, the correlation functions of observables, which are just expectation values of products of some physical observables. What I call observables are simply some local functions of the local variables on the lattice, like a spin, for instance, at a given point. These correlation functions display a rather striking behavior. In particular, when you look at correlation functions evaluated at points which are far apart enough, there is a typical power law behavior. So here the 2-point function, which is the average, the expectation value of the product of the spin variable in the Ising model at 2 different points, decays like a power law as a function of the distance, and this power law involves the thing physicists are really interested in, which they call a scaling dimension or a critical exponent. As you also know probably, what's particularly interesting about the behavior like this is that because you're looking at physics at large distances compared with the lattice spacing, you are expecting to observe universal properties. That is, values of the exponents should not depend on the lattice on which you are doing your calculations, be it the square lattice or the triangular lattice. That's what we mean by universal. And of course, all this is wishful thinking. Very little of it is proven in general. And we also believe very strongly that the properties of correlation functions such as these are described by conformal field theory, which means in particular that correlation functions such as these and more complicated, like involving 4 spins and so on, should have nice properties under conformal transformations. Now at this stage I could try to launch into trying to define a conformal field theory. There's as many definitions of conformal field theory as there are sub-communities, I think, from condensed matter to particle physics to category theory to there's more. I'm not going to launch into this at all, in fact, because I'm going to take a very narrow point of view where I want to focus only on algebraic properties. So for me, and in fact, we have to be honest, for most physicists, what conformal field theory means is not so much that you can do conformal transformations. It is that you have an underlying infinite dimensional Lie algebra whose representation theory can be used to calculate physical properties like critical exponents. So I remind you all of what the Virasoro algebra is, which you know very well, infinite dimensional Lie algebra with a central extension, which we call the central charge. It's amusing, by the way, to notice that physicists knew about this algebra many years before the field of conformal field theory really started exploding. What physicists were missing was results about representation theory of the algebra. And that's only when the results about the representation theory came that the field really exploded, because not only did we know the algebra, but we also knew which representations, which modules we could expect to observe in physical systems. So that was really what was new for us. So physicists use the Virasoro algebra, and they use another concept which is unfortunately a little harder to define, which is the conformal bootstrap and fusion. So I would like to give you an intuitive idea of what fusion means, and then I will try to define it more precisely when I move to associative algebras. So fusion in a nutshell is very simple. It is this naive idea that in a statistical mechanics model, you usually are not going to have that many quote-unquote important observables. In particular, it means that if you take 2 observables such as the spin and look at this observable at a large enough distance, which means measure correlation functions involving these 2 observables, and a third one far from the first 2, you should kind of expect that the 2 observables you have at a large enough distance should behave like a new, simpler object. That's the idea of fusion. It says, for instance, in the Ising model, that if you have 2 spins, and if you look at the spins not very nearby but at large enough distance, pretty much these 2 spins should behave like what we call the energy, which is the product, strictly speaking, of neighboring spins. So of course, if your spins are close but not really neighbors, it's not really, strictly speaking, what you call the energy. But if you look at everything at large enough distance, we should behave more and more like what you would like to call the energy. Now, I know this definition is not a rigorous definition by any means. I could appeal to higher authorities and talk about vertex algebras and operator product expansions in a more general context, but I will not need to do that. All I need at this stage is for you to have a qualitative understanding that what fusion means, because then I'm going to try to define it more precisely in the context of associative algebras. Now, a historical remark: for many physicists, getting rid of the lattice and working directly in the continuum theory, working directly in the context of the CFT, has been a great source of progress. And for a while it looked not particularly necessary or interesting to really understand in detail what CFTs as field theories or as mathematical objects, defined however you want, were related with the initial lattice models, like the Ising model on a square lattice that I started with. Unfortunately, or rather fortunately maybe, it turns out that we have had to go back to wonder about this question that we avoided at the beginning. How are really the lattice models and the conformal field theories related with each other? It's got to be complicated, because a conformal field theory is a theory that admits a vast symmetry of conformal transformations, which of course you know cannot be observed exactly on the lattice. So surely you're going to lose a lot when you try to go to the lattice and see how the conformal symmetry is emerging. Why would you want to do such a complicated thing? Well, the reason, one of the main reasons, is because we are stuck. We are not understanding very much about what's called logarithmic CFTs. And that's worth a minute of discussion as well. Because you see, in quantum field theory, unitarity, the positivity of the representations, is something that's essentially mandatory for physical reasons. And it's very nice because it implies in particular semi-simplicity, and in fact in many cases it allows full classification of the Virasoro modules that can appear in a given physical model. That was, after all, the great result of Frieden, Chu, and Schenker back in the late 80s, early 90s, is that if you knew that the central charge, the central extension of the Virasoro algebra was smaller than 1, which is a restriction, that's not such a restriction, and if you knew that your theory was unitary as a physical theory, you immediately could conclude that the Virasoro representations that you needed were unitary, fully reducible, and in fact these were classified. So all you had to do was look at the catalog of possible Virasoro representations, and you were happy. You could use the work of Rocha-Caridi or Fagen and Fuchs and solve all your models. The problem is that when you try to apply conformal field theory, not to quantum field theory, not to string theory, but to statistical mechanics, you do, in many cases, lose this constraint of unitarity. For instance, strictly speaking, the CFT that describes percolation cannot be unitary, because the observables of percolation, so to speak, are not local in the sense that you are interested in questions such as, is this part of the system connected with that part of the system? That's a kind of non-local information, and when you start thinking of it more deeply, you realize that the price you have to pay to describe such non-local observable is that your CFT will not be unitary. Now, having non-unitarity is, when you think of it, a catastrophe, because the instant you lose unitarity, you lose, in particular, non-semi-simplicity. You could have all kinds of gory, complicated modules appearing in your CFT, and in fact it's known to be the case, and in fact it's known that Virasoro in general has a representation theory that's wide. So the landscape of possible CFTs becomes extremely complicated. It becomes so complicated that we have not up to this day, and Simon will give a talk about LCFTs, maybe he'll say more about this, but we have not up to this day been able to have an approach to non-unitary CFTs, non-unitary statistical mechanics models, from the top down, starting with representation theory of Virasoro in some abstract setting, and then going down to solving the physical model. So when you can't do that, you have to go from being a bird to being a frog, paraphrase Dyson, and look at things in details. And that's what we are doing. We are trying to solve logarithmic CFTs by going back to the lattice, understanding what happens on the lattice, and trying to take the continuum limit from the lattice into the CFT, which is very ambitious, probably hopeless, but that's so far all we can do. And that's what we've dubbed the associative algebraic approach to CFTs with Nick Reed back in 2001. And qualitatively, this should not be very complicated. So now I know I'm getting into a very dangerous territory, because this is often where mathematicians stop me and I cannot ever go any further, but I will not allow you to stop me in this case. There is a very crude point of view which is obvious to any physicist, which is that, hey, you have a sort of discrete Virasoro on the lattice. It's all very simple, at least in principle. Why? Well, because if you go for an instance from the 2D point of view to the Hamiltonian point of view that Vaughan was describing, and you have a local energy density, a local interaction, a nearest neighbor interaction, which he was representing by crosses in his tensor network diagrams, typically these will be expressed in terms of some perfectly well-defined associative algebra, like the Temperley-Lieb algebra. But on the other hand, you know that in the continuum limit, in the equivalent quantum field theory, this should be nothing but the local energy density, which is the sum of the stress energy tensor right moving and left moving. And it's also rather easy to convince yourself, when you think a bit, that the commutator of two nearest neighbor generator has something to do with the momentum, so it should be like t minus t bar. So based on this, physicists have tried for a long time, and I'm not going to discuss this because precisely I want to avoid these difficulties, but physicists have tried for a long time to have a sort of limit process where they would try to define a discrete version of the Virasoro algebra using the Temperley-Lieb generators and the commutators, and sort of, if you wish, define a limit process by which the associative algebra would go into, quote unquote, and that's where the David lies, right, into the enveloping algebra of the Virasoro algebra. There's been a lot of work on this, a lot to say about this. We know how it should work, but we can't do it rigorously, and we don't particularly want to, and it's anyway very complicated. So I could say more, like I said, but I don't want to take this direction. I want to take another direction. I want to try to show you how we are going to try to avoid these difficulties and try to understand the relationship between, for instance, Temperley-Lieb and Virasoro at a rather more abstract level, going in between the frog and the bird, and how this may or may not be useful depending on the situation. Then I may go back to this question a little bit at the end. All right, so that's it for the introduction. Now I'm going to focus a little bit more on technical aspects, but not that much more. And I'm going to try to explain, first of all, in what sense we can consider that a generic standard module of the Temperley-Lieb algebra in some sense goes in the continuum limit to a certain type of module of the Virasoro algebra. And then I'll try to sustain this claim by some calculations. So let me first of all focus on what physicists will call the open case. So the point is that when you look at a periodic spin chain like Vaughan was describing yesterday, you're expecting that in the continuum limit there should be two Virasoro algebras, left and right movers propagating on your chain. And that's of course complicated because two Virasoro algebras is even more complicated than one. And the fact that you have two Virasoro algebras is because the fields formally should depend on z and z bar, treated essentially as independent coordinates. Now there's a first trick to reduce the difficulty from two Virasoro algebras to a single Virasoro algebra, which is to consider the theory near a boundary, or after a logarithmic conformal mapping on a strip instead of considering it on a cylinder, or if you wish, have a Hamiltonian that acts on a finite interval, open, instead of acting on a circle. This is the exact setup for the Temperley-Lieb algebra, and that's definitely where you should start focusing if you haven't understood what I was talking about so far, because this is something everybody knows. So many simple statistical mechanics models in the case of open boundary conditions, meaning where you don't close the system on a circle, are described by the Temperley-Lieb algebra, which is this algebra with a parameter m, and the parameter m is interesting for physics. If m is between -2 and 2, then the statistical mechanics models are critical and are described at large distances by conformal field theory. All right, so this algebra is well known, and it has standard modules which are also well known. So if you have n strings, which is like n spins in a quantum spin chain, it is known that the modules are parameterized by a single thing, which is the number of through lines propagating through the system that you prevent from contracting. This number of through lines can be anything between 1 and n, although it must have the same parity as n, because of the constraints of Temperley-Lieb, and the corresponding modules are well known. I will call them Wjn, and they have a dimension. That's the difference of two binomial coefficients. And the important point is that for Q generic, remember I said m would be -2, between -2 and 2, which means if I parameterize m by q plus q inverse, that q is a complex number of modulus 1. If q is generic, meaning it's not a root of unity, then these modules are irreducible. Okay? Good. Now, here is one thing we know almost rigorously. I hesitated about the word rigorously. I would say we know it for sure, but I think it can be made rigorous if anybody is interested. if you set q is e to the I pi over x, where x is an irrational number, because I said q would be generic, we know, first of all, in what sense, I'll explain exactly why, what the sense is, that the continuum limit has central charge 1 minus 6 over x, x minus 1. So for instance, q is e to the I pi over 3 is m equals 1 is percolation, which corresponds to c equals 0. And I remind you in that case that the Katz formula, the formula giving the conformal weights, which are the eigenvalues of the generator L0, in the degenerate case, meaning representations that have a null vector, which are different from the Verma modules, is HRS is xr minus x minus 1s squared minus 1 over 4x x minus 1. We know, and that's something that's independent of Temperley-Lieb, of course, that's pure Virasoro. We know that for these values of the conformal weight, the Verma module admits a singular vector at level HRS plus RS, and there is a way to get rid of that singular vector by taking a quotient which defines what's called the Katz module. It's an irreducible module. All right, so I have modules for Temperley-Lieb here, I have modules for Virasoro there. Now I'm going to explain why I say that one is, in a sense, the continuum limit of the other. How do I do this? Well, first I'm going to introduce a lattice Hamiltonian, which is the one you saw yesterday in von Jones-Stokes. And then I'm going to claim something, and that's something which I think can be proven in all mathematical rigor, even though it hasn't been done. I will do the following. On the one hand, I will calculate on the standard module of Temperley-Lieb a certain object, a kind of character, which is the trace over this module of e to the minus beta. So beta is a parameter that I'm going to choose in a minute. H is the Hamiltonian, and then I'm going to subtract to H something which is a little bit tricky to explain, but it's very simple in practice. It is simply the ground state energy of the fundamental. As you know, energies in physics are not defined absolutely. What's really defined is differences of energy. And whenever you worry about the energies, the eigenvalue of the Hamiltonian, you have to decide what the origin of energy is here. So this thing is just to define the origin of the energies conveniently. It is chosen in such a way that for an infinite system, the state with the lowest energy, and then energy is the eigenvalue of the Hamiltonian, this energy is 0. You can forget about this if you're confused. So I take this limit as n goes to infinity. So of course I have more and more and more and more strings in the Temperley-Lieb modules. H has more and more and more generators. I don't care. I know how to calculate it for any n anyway. So I calculate it for any n, I send the limit, I send n goes to infinity, and at the same time I'm going to send beta to infinity, so that q is e to the minus pi beta over n remains finite. Okay? In this limit, we know that this trace becomes exactly the character of the Virasoro algebra over the corresponding Katz module. That is, this lattice object becomes the character of, which is trace of q to the L naught minus c over 24, calculated over a certain module of the Virasoro algebra, which is the Katz module, k1, 1 plus 2j. So, roughly speaking, this module should, in some sense, in the continuum limit, become a module for the Virasoro algebra with central charge, this, with conformal weight h1, 1 plus 2j, where the HRS were given in the Katz formula, and that's the module which is also simple, irreducible in the continuum limit, the Virasoro module, which is in fact the Katz module. That's a very weak sense in which we are absolutely convinced, but this result is pretty solid, that the trace of something on the lattice model, when you take n goes to infinity, become the trace of q to the L dot minus c over 24 over the Virasoro module, which suggests, yeah?
Just the confusion I have. So the lattice model is classical.
Yeah.
Okay, so when you write trace, it's just the sums. But
It's just the sum over all the eigenvalues. It is perfectly well defined. N is always finite. I calculate it for n finite.
Okay.
I take n goes to infinity.
So in what sense do you have a proof of that?
I'm sorry?
In what sense do you have a proof of that?
Well, physicists prove we control all the steps because we calculate everything. But if you ask me,
So, I mean, do you get the, you'd have to use the beta ansatz or something to get...
yeah, you have the beta ansatz, you have proved that the beta ansatz is complete, and you have analysis of the asymptotic behavior of the beta ansatz equation in the limit n gets large. Now, I'm not saying it's a proof in a mathematical, I mean, it has to be worked on, but I think this is a no-brainer. I'm sure it can be made into a proof.
Numerics to justify it.
Absolutely, yeah, it's undeniable numerically. All right, so the question is in
Cuts modules among these non-unitary things, so something like non-star representations, or are the cuts modules still reasonable star
Sorry, can you repeat that?
of the
Sorry.
Virasoro algebra?
Can you repeat
You
that?
mentioned
You
before
have a
that
positivity.
you mentioned before that the
Yeah.
Virasoro algebra you need some non-unitarity there.
Oh, welcome
Will it
later.
happen here or?
Welcome later. In this case, everything is unitary. In this case,
No,
Wj is simple.
not on the Temperley-Lieb side.
Wj is simple, and the Virasoro module is simple, and all the states are positive, positive square number. So it is unitary. Am I right?
On the,
Am I
on
wrong?
the Temperley-Lieb side, you've got irrational, so you don't have the positivity there.
But for Q irrational, it's all positive? No, there are signs. Yeah.
Yes.
Yeah, that's a good question. No, you're right. Okay, you're right. So that's same for Virasoro. It is not positive, but it is simple. No state of square norm 0. Thank you. Absolutely. Yeah. All right. So this kind of observation can be generalized in some sort of zoology of the correspondence, can be generalized to all kind of modules and all kind of algebras, which I'm not going to get into. I want rather to get into something else. So like I said, there are ways to think of this problem. One is to try, once you have this kind of identification, to go further. This looks like, in a certain sense, H becomes L0 minus C over 24 in the continuum limit. Can you get a guess for the other Virasoro generators? Can you start investigating the Virasoro commutation relations, starting from the Temperley-Lieb and so on and so forth? This is something that has been tried, and I wanted to just flash a formula that's been used with great success in building lattice approximations to the Virasoro generators. And this is the kind of formula where I could get stuck, so I'm going to pass on it quickly. But let me just say that physicists have a hierarchy of approximations, and the way they see it working so far is that at n finite, there's a lot of approximations of the Virasoro generators, which in a certain sense should all go, and I don't know in what topological sense, I mean in what topology they should go, to the Virasoro generators in the continuum limit. This is something I could say more about, but like I said, I want to avoid it. I just wanted to mention it. Because I want to do something else. I want to stop trying to identify Virasoro directly, and I want to go back to the beginning of my talk, where I said there are two important things in physics that we use when we do conformal field theory. One is representation theory of Virasoro, the other one is conformal bootstrap and fusion. So the rest of the talk is devoted to an effort to try to do fusion a la operator product expansion on the lattice and see whether it gives me another weaker but maybe more controllable correspondence between associative algebras and Virasoro. So this is what I'm going to start discussing now, fusion. Now, I told you that in the context of lattice models or quantum field theory, when you do operator product expansion, when you do fusion is you bring two fields close together and you look at them, so to speak, at large enough distances. When you think of it a bit, it's rather easy to see what the equivalent construction should be in the context of associative algebras. What you should take is two Temperley-Liebs, one acting on n1 site here, one acting on n2 sites, and merge these two into a third, which corresponds to looking at these two at large enough distances in my intuitive picture. And it's very easy to do if you have a Punt's diagram, like we are familiar with in string theory. So what we're going to do is imagine we have two Temperley-Lieb algebras on n1 sides and n2 sides, and then we're going to glue them in order to make a Temperley-Lieb on n1 plus n2 sides. And the question we're going to ask ourselves is, well, if one module Wjn at, so to speak, a continuum limit, which was this cat's module, if another module for J2 and 2 has another continuum limit, which is another cat's module, can I compare the fusion on the lattice with the fusion in the CFT? And that's very easy to do, because we know how to do fusion of Temperley-Liebs. We know that we have a Temperley-Lieb here and a Temperley-Lieb there. All we need to do is glue them by adding the extra generator and induce a module on Temperley-Lieb n1 plus n2, which is n, starting with a module on Temperley-Lieb n1 and a module on Temperley-Lieb n2. So that's very straightforward. It's not particularly interesting, but I want to talk about it as a way forward. So it's very easy to do calculations just by using some sort of Schur-Weil duality with SU2Q for Q generic, for instance. And what you see when you do this kind of fusion is that, of course, if you have a module on n1 strings with two J1 non-contractible strings on the left, a first Temperley-Lieb module and a second Temperley-Lieb module, if you look at the induced algebra, it's very easy calculations, that you're going to get a direct sum of modules of Temperley-Lieb now on n1 plus n2 sides, with values of j running between j1 minus j2 and j1 plus j2. This is, sorry, I keep being confused between the buttons. This is totally obvious, because when you bring together two modules, you can contract strings between one and the other, or not. So j runs between j1 minus j2 and j1 plus j2. A trivial result, but it shows that we're on the right track, because in conformal field theory, remember I wanted to associate to this module a conformal field of weight 1, 1 plus 2j1, and it's certainly true that in the language of OPEs, if I do the OPE, the operator product expansion of these two fields, I know similarly that it will get a sum over phase 1, 1 plus 2j. So at least this is compatible, okay? It's not taking us very far, but it's useful. It has been, and now let me open a parenthesis, it has been very useful, in fact extraordinarily useful, in the cases when Q is a root of unity. So now I come to my business about non-semi-simplicity. The point is that when Q is a root of unity, of course, we're going to have a bunch of modules which are not fully reducible. And for instance, Wj, the standard module, it now admits is not irreducible anymore when Q is a root of unity. And by the zoology of the modules you can get, these are completely understood. And in particular, we have been interested, for reasons that will come clear in a minute, in what's called projective, the projective modules in this case, which are gluings of two simple modules. So when Q is a root of unity, if Q is e to the I pi over p, which corresponds now to a central charge from the minimal series, 1 minus 6 over p minus 1p, we know that these projective modules have the following structure. They're gluings of two simples, and they're made of 4 simple modules with arrows going like this. Now, this is on the algebra, associative algebra side, and there are more modules which I could also talk about. I will just focus on these. Why? Because we can play the same game. We can ask ourselves what is the continuum limit now of these projective modules at Q a root of unity, and the same exercise can be played, and what you observe rather easily is that the continuum limit of these gluings of two simple modules is now the gluing of two CATS modules, but these are well known in logarithmic conformal field theories. There are what is called staggered Virasoro modules. So the correspondence at the level of the traces still works, but now what's really exciting is you can push this further. You can ask yourself about the fusion of projective modules in the way I just defined up there. So now I've made two Temperley-Liebs, and now I put projectives on the two sides, and I look at what the fusion is, and I can calculate that. I mean, a lot of people have worked on that. There's a big community who has worked on this thing, and you can compare with the fusion of staggered Virasoro modules, which can also be done at the level of the Virasoro algebra, in a much more complicated fashion. And of course, it works. It works beautifully. That is, you can still calculate the fusion of these modules of the Virasoro algebra using the associative algebra calculations, which are much easier because, in particular, they are essentially independent of n. You can take an n rather small, do calculation numerically using brute force, and then obtain conjectures about fusion of Virasoro modules. So that's a direction that many people are working on right now, and using this kind of ideas, there certainly be a lot of progress in the analysis of boundary LCFTs. That is, we know much more about the operator product expansion in LCFTs than we ever would have by importing these results from associative algebras. So that's something, first message of my talk. Second message of my talk is that, of course, as physicists, you can do a lot of calculation, and you can, in fact, conjecture a lot of results for these fusions. Some of them are not known to mathematicians, I think, but there are a bunch of conjectures that are now running around the physics community. And that's an example. That's the general formula for the fusion of two projective modules, which is quite complicated. And I think it's correct anyway. All right, so now the second thing I want to discuss in this talk, after having tried to get this message across, this second message across, the third message I want to get across is that we are not really interested in Temperley-Lieb, we're interested in affine Temperley-Lieb. Because really what we would like to do is study theories on an annulus. So the challenge for us, and I'm not quite sure whether the answer would have been obvious to mathematicians or not, is that we would like to do this fusion business not for the boundary case, but for the bulk case. So we would like to do it when we have Temperley-Lieb acting not on a segment, but on a circle. That brings us to another algebra, which is the affine Temperley-Lieb algebra, which is essentially the same as Temperley-Lieb, except you have one last generator that closes the system, and then, to be a little bit more technical, there's also now the translation operator, which is represented here. Every string is moving one notch to the right or one notch to the left, and going around if necessary. All right? Like we had in the open case, in the closed case, we also have a correspondence between affine Temperley-Liebmodules and Virasoro times Virasoro bar modules. I'll explain this later. I want to start, because I see that time is running short, I want to start by the thing I want to discuss, which is doing fusion in the periodic case. You see, in CFT, we do how to do fusion not only near the boundary, but also in the bulk. We can bring two fields that depend on Z and Z bar next to each other in the bulk. How can you do fusion for affine Temperley-Lieb? This is a challenge we've had really for quite some time, because you cannot do the Pern's trick anymore. You can take two sheets and glue them into a third one. That's very easy. But if you have two cylinders, how are you going to glue them? You can devise various ways to glue them. The problem is that typically, in order to glue them, you're going to have to first cut open and then glue. And the question is, how are you going to cut open in some sort of universal way? So there's been a bit of work about this, and this is what I want to explain. In fact, the way to do it is quite simple. I suspect it's canonical, but the problem is that it's not very satisfactory. So I'm hoping that maybe some of you will have suggestions about how to do this in a better way. So I repeat, what I want to do is glue two modules of affine Temperley-Lieb, both of them defined on cylinders. The way I'm going to do it is a bit dumb. I'm going to use the fact that because I have Temperley-Lieb, I have not only Temperley-Lieb, but also have solutions of the break group equations, which are obtained by making linear combinations of the identity and the generator EI, and I represent these two generators like this, and of course, as usual, they satisfy the braid variant of the Yang-Baxter equation. Now, the way we're going to do this is very dumb. We're going to take our two cylinders, and then, for instance, the translation operator on the first n sites, we're going to extend it to the whole system, which is made of n1 equals 3 and n2 equals 2 sites, by simply saying that what we want to do is shift the first string to the second position, the second string to the third position as before, right? That's what I would have in the ordinary definition of the algebra. But now I have added my new cylinder with N2 strings, well, the way to handle this is I'm just going to say, in order to shift my third string to the first position, I'm going to pass it above the other two. I could also pass it below. I'm going to choose pass it above. That's what I'm going to do. And similarly for U2, the generator of translations on the second half, I'm going to say, well, I'm going to have to, in order to pass my second string around and back in first position, now that I have the N1 strings, I'm going to just pass under them. This is how I'm going to define the embedding of affine TLN on N1 sites and affine TLN on N2 sites into affine TLN on N1 plus N2 sites. Similarly, for the Temperley-Lieb generators that connect the first and the last site on N1 or the first and the last on N2, I'm simply going to define them on N1 plus N2 sites by doing this obvious trick that I go above in one case and I go under in another. In a sense, this is trivial. In another sense, it's unbelievably complicated. That's one way to do it. It is canonical in the sense that it does not depend on where you're cutting open, so to speak. You're not really cutting open, you're kind of merging by passing above under. All right, so a bunch of things I don't really need. The point now is we want to do calculations. As always, physicists want to do calculations. So we want to do calculations for the standard modules like we did for the ordinary Temperley-Lieb. In the case of a fine Temperley-Lieb, it's more complicated. The standard modules depend on two parameters, as many of you know, I'm sure. One is, again, the number of strings going through. But now, because you have an annulus, you can go around the annulus. So there's a kind of Fourier momentum associated with going around the annulus, which, so we're using the notations of Graham and Lehrer, although many other people have worked on this. That's the variable z, and z is essentially the phase you get when you take your non-contractible lines and you go around the annulus. In fact, strictly speaking, z to the 2j, but it doesn't really matter. The point is, there are modules which depend on two parameters, j and z. The dimension of the modules doesn't depend on z, but they are not isomorphic for different values of j, and now the dimensions are simple binomial coefficients instead of being differences of binomials. All right, so now we have done a lot of work in doing the fusion, and I thought this would be interesting for this community, maybe, because there's room for a theorem, but we have not proven a theorem. Here's another quote of Bertrand Russell I really love. The method of postulating what we want has many advantages, but are the same as the advantages of theft of an honest toil. I replace postulating by conjecturing, which is what physicists are good at. So here are the results. Believe me, they're true, meaning we've checked them on very big systems with a lot of work, but we have absolutely no proof whatsoever. I'm sure a proof is possible, but I don't know how to do it. I mean, Gus Lehrer seems interested, but I don't think he's produced a proof yet. So the fusion of these affine Temperley-Lieb modules is definitely very disappointing in the sense that, in contrast with the fusion of the ordinary Temperley-Lieb modules, it doesn't give rise to a sum on the right-hand side. It's very constrained, and when you think of it a little bit, you understand why it's constrained. It's because when you embed U1, the translation generator, for the first half into the whole thing, and U2 into the whole thing, you have a kind of compatibility condition that you have to be very careful with, which means in practice that you cannot do fusion in general, or rather that the fusion is zero, except in a bunch of special cases. So if you give J1 and J2, there are values of Z1 and Z2 for which the fusion can be done, and you get indeed a single WJZ module on the right. If you don't satisfy these matching conditions, so to speak, then the fusion is zero. So that's what we get from the lattice, and then we're going to see what it means in the conformal field theory in a minute. So my collaborators who are more mathematical than me are very excited about categories, which I'm not. So I'm not going to talk about this very much. I insisted about under, above. Of course, you can switch above and under. So I defined one fusion, but in fact there's another fusion, hence the question of whether we have braiding, a braided category, and all that. Another technical remark, we have puzzled about Zelevinsky's tensor product for years. Definitely it's easy to do fusion of affine Hecker algebras. It seems much harder to do fusion of affine Temperley-Lieb algebras. I'm not sure I fully understand why. I understand intuitively why, in the sense that the restriction from affine Hecke to affine Temperley-Lieb does not seem to be compatible in general with the Zelevinsky tensor product, but I would like to see this be made more explicit. Maybe some of you know about this. Arun Ram seemed to know about this a bit, but I'd be very happy to have more information. Anyway, there's a room for a theorem, which we are not going to prove. Sorry. Now let's go back to CFT to conclude this talk. What happens about our idea of doing fusion in the closed case? Well, many things work similarly. So in the open case, like in the open case, we take the Hamiltonian, that's the sum of the EIs. And now we have not only Hamiltonian, but also momentum, right? And we can similarly define our trace over finite dimensional modules of affine Temperley-Lieb with two objects, which are the Hamiltonian and now the momentum, and we can calculate this limit n goes to infinity, and we observe that we get a trace of q to the L naught minus c over 24, 2 bar to the L naught bar minus c bar over 24, this time over modules of Vira0 times Vira0 bar. So similarly to the open case, we have a sort of correspondence between modules of affine Temperley-Lieb and modules of Vira0 times Vira0 bar. Very crudely speaking, by the way, in the open case, we had only one number, which was j, in the modules of Temperley-Lieb, and we have only one number in the Vira0 modules, which is j. In the affine case, we have two numbers for the simple modules of affine Temperley-Lieb, wjz, and of course we have two numbers for the Vira0 algebra. You have HRS of the Katz formula, so very crudely speaking, that's where you should be looking for a correspondence, and there is therefore some correspondence like this. Which values exactly of h and h prime you obtain, I decided not to put on the slide because it's a bit complicated, but certainly morally that's what happened. So now my idea was, oh well, we have done fusion for the affine Temperley-Lieb, we know what modules this corresponds to in the continuum limit. Let's see whether I can reproduce the fusion in the non-chiral case by using this trick. It is very challenging for us because we are all trying to understand OPEs of logarithmic CFTs in the bulk, not on the boundary. And we don't know what these OPEs are. They are very complicated to calculate, except in some very simple cases. So this was a hope that this trick would do the job. It does not, and I need 3 more minutes, it does not, unfortunately. So what you see when you take the correspondence between these affine Temperley-Lieb modules, these Vira0 bar modules, and when you translate this unpleasant result, by the way, it doesn't depend on n1 and n2, of course, that's the beauty of it. When you translate this result into what it should mean for Vira0 in the limit n goes to infinity, you get something that's meaningful but disappointing. You get this fusion. Imagine you take a first field phi with conformal weight h and h prime for Vira0 and Vira0 bar, and then you do the fusion with another wjz. Well, in general, you'll get 0, except when the j and z of the second module correspond in the continuum limit to the same conformal weight for the left for the Vira0 part as you had for the Vira0 bar part for the first module, and then another one for the right. And what our fusion is doing, very disappointingly, because it's utterly useless, at least it seems, is that we are gluing the right movers from a field with the left movers from another field, projecting onto the identity and getting Vira0 h times Vira0 bar h double prime. So that's all what fusion is doing. It's not at all what we wanted. We wanted a complicated sum with many other fields, like we have in the continuum limit. So we are puzzled. We don't know how to do a good fusion for a affine Temperley-Lieb, and we take us our suggestions. All right, that's essentially the end. Conclusions, yeah, I have plenty of questions for mathematicians. This business of fusion in the affine Temperley-Lieb case is just the tip of the iceberg. We're interested in fusions for the boundary Temperley-Lieb algebra of various types. Maybe another way to do fusion for affine Temperley-Lieb. I don't know about this. I should have said also that affine Temperley-Lieb, strictly speaking, is infinite dimensional because of this business of winding an infinite number of times around a cylinder. What I described by finite dimensional modules obtained by taking a quotient, saying that if you wind everybody once, it's the same as not winding up to some scalar factor. But the algebra also has infinite dimensional modules. For various reasons, we're interested in the fusion of the infinite dimensional modules. If anybody knows anything, I'm interested. Physicists have to do a lot of representation theory to understand in detail the relationship between lattice models and their CFTs. So there's still more that we are learning. I hope there is more that we can do. I wanted to illustrate finally the kind of exercises that we are getting into because we need this information. So I gave you only one half of the story here, which is I focused on a fine Temperley-Lieb or Temperley-Lieb. But of course, when we're going to have a physical spin chain, we're going to have more than this. We're going to have bimodules because typically the spin chain will have the action of a symmetry group, a quantum group, or in many cases a supergroup. Now, in the simple case, technically simple, meaning simple, the decomposition of as a bimodule over the Temperley-Lieb and the centralizer is very simple. It's just a direct sum. But in the non-semi-simple case, it's much more complicated because both the modules of the Temperley-Lieb and the modules of the centralizer are not simple anymore. So there are complicated diagrams, and we are working on trying to elaborate this kind of diagrams because, so to speak, once we have these diagrams, we can relate the physical properties of states, say here, with those of states, say there, by using a combination of arrows along the centralizer direction and a affine Temperley-Lieb direction. So this is in fact very useful, and it's an exercise which I'm sure is very mathematical, and probably some of you know quite a bit about this. So this is another direction in which people are working, and that's it. Thank you for your patience.
So, in the unitary case, the fusion of these affine Temperley-Lieb modules is a very well-oiled affair, and you get the sums that you probably want.
Yeah, we get in that case totally meaningless stuff. I mean, we know the fusion in the conformal field theory, you mean? And when we do the fusion of the affine Temperley-Lieb modules, we don't get what we want in the continuum limit.
You will if you do the fusion in the way that's done.
If we did the fusion the proper way, yes.
So that's what I'm saying is that's perfectly understood.
You mean the fusion of the affine Temperley-Lieb modules? All right. Well, I'm
in the unitary case. Now
in the unitary case.
So you know you draw. It's all picture stuff, and you just draw the picture for the fusion, and then you quotient by these relations, and everything collapses, and it's very nice. So I would say the thing to do for your logarithmic case is to try to mimic that. Just that the collapse of the pictures will be much more complicated because you'll get these non-semi-simple parts.
Yeah.
Coming in, but it should be possible, and just there is probably.
But you're using the structure of the modules. I mean, you're using the fact that you have simple modules when
Yes.
you do the fusion.
Very much so. Yeah.
So it's not it doesn't use lines. It uses simple.
No, it doesn't use that crossing. You just draw the pictures, and it works. I mean, there's a result due to a whole lot of people about the affine. In the unitary case, that the affine representations as a category is equivalent to the Drinfeld double of the thing you started with.
I
so
see
you
what
have, you have the fusion that you want.
Yeah.
And there's a big industry going on now that might interest you even more. That people doing it in the infinite dimensional case,
I see.
where the things are infinite dimensional, it's still a fusion.
I see.
So that's big. A lot of people.
Well, that's very interesting. Okay.
But the non-semi-simple case would be much more complicated.
Well,
But it's probably a story that you just by following what happens in the unitary case, you could.
okay. Well, that's exciting. All right.
Function?
Well, you described the fusion in the Temperley or affine Temperley case, but the fusion on the versora part, what kind of definition you use over there?
Yeah, that's a good question. I think maybe someone will discuss that. No. Oh.
I'll be glossing over it.
Yeah. I mean, there are various ways that physicists. I mean, the best context would probably be vertex operator algebras, and extensions of vertex operator algebras to the case where the conformal weights are not integer, which is really what we're having here. There is also an abstract algebraic way of defining the fusion of Virasoro modules independently of talking about fields, coordinates, vertex operator algebras, and so on, purely algebraic, a sort of tensor product of Virasoro representation. It's not quite a tensor product because the central charge remains the same. When you do tensor product of two Virasoro representations, naively the central charge would change. So there is something, it's called Gaberdian-Nahm algorithm. And it has been formalized quite a bit, right? I don't know what the best mathematical reference would be, but it exists, but it's not simple.
For instance, is it associative?
I'm sorry?
Is it associative?
It is possible, yeah.
You have a question?
Yeah, what is the role of integrability to group representations? The Virasoro has something to do with the geomorphisms, and also the Thomson group, which appeared in Vaughan's talk. This might also be a way to understand which representations of Virasoro are relevant. Maybe it's not the right way.
Yeah, I would have various things to say. I mean, in a certain sense, I think some people would disagree with this, but I tend to think of a conformal field theory as an integrable theory. Meaning it's possible to build a set of quantities in involution using the enveloping algebra of the Virasoro algebra. So in a sense, a CFT is always integrable, but integrability does not seem to play a role here. And nowhere do we really use integrability except that we can calculate things in the case where the lattice model is integrable, but
I meant integral in the sense of integrating from Lie algebra to a Lie group-like thing.
I see.
So
I'm
if
sorry.
geomorphism groups
I
have
see.
some
I
sort,
see.
like Thomson's group or something. I'm not sure this appears in the Virasoro algebra.
No, I don't have much to say about this. I mean, it's very hard to understand the meaning of conformal transformations in logarithmic CFT in general, which I think must be closer to what you're asking. So no, I have no idea. We've seen all kinds of modules appearing in physical models. I think in a sense, probably all the relevant modules will be projective modules. Whatever this means for Virasoro, that's another question. That would be the only constraint I've seen so far. Nothing else seems to come to mind, but that's a good suggestion. Simon?
Yeah, I was just the affine fusion products that you were computing. These were done at non-root of unity, or
Non-root of unity, yeah.
have you looked at root of unity?
Believe me, it's complicated. I mean, this result is pretty complicated to obtain. I mean, maybe it seems simple. I don't know. I certainly didn't see it in the literature. But so what you're suggesting is, okay, there are two levels. One could take Z non-generic, but Z a power of Q. So we know how to do this, more or less. We could take Z and Q non-generic, then you can do this for the simple quotients quite easily. For the whole complicated, ugly modules, no, I have no idea. But it's fun. It will be fun. All right.
Are there other questions?
All right.
Let's thank Hubert for a very interesting talk.